Welcome to a presentation on photochemical machining. The main objectives of this presentation are to understand the basic principles of photochemical machining process, to determine a proper process sequence, and to understand the applications of PCM. To understand this further, let us now look at a video of the process.
The first thing that needs to happen for a part to be chemically etched is for there to be artwork generated. Drawings are taken from computer data and photo-plotted onto film, creating areas on the film that are either black or clear. Depending on the type of photoresist being used, either the clear areas or the black areas will be the image of the desired part. Generally, there are two pieces of film created that are aligned precisely front to back. Metal is then selected, and sheets are cut to match the size of the film created. The metal is then cleaned to remove any residual oils and oxides. It is very important to have clean surfaces on the metal to make sure the resist that will be applied will adhere successfully. The sheets are then coated with the photosensitive resist. The resist is sensitive to UV light and resistant to acid. After the resist is applied, the material is then placed between the two pieces of artwork that have been created. The resist-covered sheet is then exposed to UV light to create the desired image on the coated metal. Generally, where the light shines through the clear areas of the film, the resist is exposed and becomes hardened. Where the resist is shielded from the light by the black areas of the film, the resist remains soft. After exposure to the UV light, the sheets are put through a developer where the soft resist is dissolved away and the hardened resist remains. The sheet of material will then have resist remaining in the areas where the material needs to remain, while the rest of the sheet has exposed metal where the material is to be removed. The next step is to have the sheet put through an etching machine where etchant is sprayed on both sides of the sheet. Where the etchant comes in contact with exposed material, the metal is dissolved. Where the resist has been applied, the material will be protected from the etchant. When the sheet is finished etching, the remaining resist must be removed. This is done by applying resist stripper, which dissolves the resist. The result is the finished etched part.
From the video, we understand that the material not protected by the resin is dissolved by the acid, thus giving us the final product of required shape. The figure shows the development of etch profiles. Note the ability of half etch in figure A, which upon continuing gives the conventional hole profiles in figure B, C, and D. You may note that there are two types of hole profiles, the conical hole in figure E and the tapered hole in figure F. Let us now look at process capabilities and dimensional limitations of PCM. The PCM can manufacture a wide variety of precision sheet metals. PCMI standard specification D300 is followed for industrial manufacturing. The following parameters are dependent on thickness of the metal, T. The minimum diameter of the hole, Dmin, which is 1.5 T to 2 T for thickness greater than 0.025 mm, and it is 2 T to 4 T for thickness lesser than 0.025 mm. The minimum metal land width, Wmin, which is 1 T for thickness less than 0.125 mm, and it is 1.25 T to 2 T for larger thickness. The minimum inner corner radius, Rmin, is T, and finally the minimum outer corner radius is 0.75 T. Get some design guidelines. The maximum measured thickness varies with the metal being etched and profile requirements. In general, the metal thickness is 2 mm and the dimensional tolerance for this process is 0.1 T. The tolerance for center to center and pitch to pitch dimensions are 0.05%. Few more guidelines. It is advisable to have a 15 mm border around the edge. We can use different colors for half etch and full etch sections. We can also have a minimum line width of 0.15 mm for half etch and thickness of the material for full etch. Make etch bandwidth between 0.5 to 1 mm for ideal results. Let's now look at some alternate manufacturing processes. There are a number of other alternate manufacturing processes which can substitute PCM. They are computer numerical control machining, photoelectroforming, laser beam machining, wired electrodischarge machining, and stamping. Let us now look at some limitations of PCM versus other techniques. The limitations for PCM is aggressive chemical etchants are required for more corrosion-resistant metals. For PEF is that the material options are limited. In the case of LBM, it is a generation of heat-affected zones, while for WEDM, it is that each aperture requires wire breakage and rethreading. And finally, for stamping, it requires grinding. Now let us compare PCM with metal stamping. From the first point of comparison, we understand that PCM is economical for complex parts of small to medium quantity. From the second point, it is evident that PCM has an advantage over metal stamping in terms of cost and lead time for making prototypes. PCM also does not require final finishing, and it also does not interfere with the material properties. Finally, we can say PCM is more versatile. In conclusion, we can say PEF is significant for extremely thin metal parts. WEDM is economic for small batch sizes of thin components. Stamping is cost efficient for large batch sizes. And between LBM and PCM, PCM is a better process to produce complex parts of medium batch size. The compatible materials are bronze, titanium, cover, and some that have magnetic properties. The photoresist material is an aqueous dry film. The economic batch size is minimum 100. The production cost depends upon the material and in general varies from $5 to $10 per pound. Thinner materials cost more. For instance, stainless steel of 0.001 inch thick costs $50 per pound, whereas 0.0005 inch thick costs $100 per pound. The cost could shoot up to $150 per pound for materials like molybdenum. The cost of the photoresist material is a constant. PCM has a wide variety of applications. This process is used to produce intricate shapes in modern quantities.